So today I will be speaking to you, as the title says, about seeing the infinite. It's a bit of a bridge between art and projective geometry, though mostly projective geometry. But nevertheless, start with a distinction, which is to say that when we talk about the infinite, at least among philosophers, I am one of those, believe it or not, philosophers tend to think about the infinite as concerning magnitudes, concerning what is infinite in size. And I want to talk about a different way of thinking about the infinite, which is the way that it emerges in geometry. And those of you who are more concerned with art than mathematics, so what is happening here? My PDF has died. Let's just try that all over again. It's probably nothing. There we go. So those of you who know about art, so this is a painting that you find at the Louvre. I thought it was nice to find something. And here you see an example. This is from Giotto from the 14th century. And this is before the methods of projection were well understood, so that you can see, as everyone who works in art knows, the basic flatness of the picture. There's no, at the time, way to be precise the sorts of dimension that you want. So in particular, you can see at the very top of that, the flatness instead of the later beauty of perspective that you will see, for instance, at the world's most unlooked at painting, the Wedding at Cana. Those of you know that this is a painting that is the other side of the Mona Lisa here at the Louvre. So this is the biggest painting in the Louvre, but everyone has their backs to it all the time. And you see that the perspective is much improved in this picture because they have learned the methods of projection, of vanishing points and the like. So these are all ideas that are well known to artists, and I won't dwell on them. But what I do want to dwell on is the way in which these methods of perspective give us insight into the infinite. So I've been scared as people have been quoting Panofsky the last few days, or rather yesterday, hoping they weren't going to steal my quote. But here's Panofsky talking about what's happening in these works of Giotto as compared to later artists. So Panofsky writes, the space of Giotto and Duccio corresponded to the transitional high scholastic view of space. Their space was gradually being superseded by true central projection, with its infinitely extended space centered in an arbitrarily assumed vanishing point. The result was the concept of an infinity not only prefigured in God, but indeed actually embodied in empirical reality. And it's that last part that I wanted to focus on today, the idea that in these works of art which have taken on the methods of projection, we are able to embody the infinite. We can see the infinite. And I want to talk about how this idea, familiar to us from art, also has life in mathematics. So the familiar way of making the transition is to think about the way in which we can model a tiled floor. Here, everyone is familiar with the idea that there is a horizon line at the top where the parallel lines that we are modeling fade away. And in order to make this model work out right, the Italian painters, for instance, in the fitness treatise by Piero, found a way to extend those parallel lines, as I've shown it. In fact, this is a diagram from him, more or less. The lines meet at a point. So there is an illusion, obviously, being played on us, and of course we need to talk more about why we say that there is an illusion in seeing the infinite, and we will. But for the time being, you see that we have lines that, to create the illusion, parallel lines that are made to meet at a point, in fact, infinitely far away, according to the theory. So with this idea modeled for us by the artists, we were able to study this from a mathematical point of view. And the first one to do so with dedicated seriousness was Desargues, French mathematician who published very little. And what we have of his invention of projective geometry is in this text from which I've quoted from 1639, which is just a potion, that's to say, just a kind of notebook in which he sketched these ideas. It's very difficult to read this text because it's written in botanical terminology. It seems that he was a kind of flaneur and wanted to express his thoughts in a way that were very difficult to understand. So instead of talking about lines, he talks about trees and the branches of these trees and the leaves on these trees. But if you can get past all of that botanical notation, you'll see that he invents projective geometry. He tells us that in this work, every straight line is, if necessary, produced to infinity in both directions, and to convey that several straight lines are either parallel to one another or are all directed toward the same point, we say that these straight lines belong to the same coordinates, which will indicate that in the one case as well as in the other, it is as if they all converged to the same place. And here, the idea that lines, all lines, including parallel lines, converge to the same place, is to say that at infinity, for Desargues, we add points to regular space. We add points at which these lines intersect at infinity. And we also add a line at infinity on which all of the points at infinity are situated. So in doing so, Desargues creates a new geometry, which we nowadays call projective geometry, because Desargues was able to study systematically which properties are invariant under projective transformations. That's to say that if you look at, for instance, this example of a projective plane, or at least a kind of model of a projective plane, you'll see that distances are distorted. You'll see that parallelism is distorted. You can also see that that order is distorted, although that's not evident from this particular picture. Angles are distorted, but what remains constant is the incidence of lines and points. And so projective geometry studies incidence relations between lines and points, and it does so while adding points at infinity, and it does so while adding a line at infinity. And so we can characterize projective geometry in a word, or in a small phrase, as the study of projective invariance, which is to say, more or less incidence, and there are a few other relations that are also projectively invariant. So that's the theory of projective geometry. But what happens is that Desargues writes this text. It's written in a very strange way. It's read by very few people. It's read by important people like Pascal and Descartes, but they don't do much to publicize it, and it fades away. And what does take the scene instead is analytic geometry, in which one brings to the forefront methods for finding equations for curves in space. And this is just an example of a textbook from the early 18th century, in which you see that the presentation is given first in a synthetic way, in which there is a figure, and then next there is a proof that is done by equations, so an algebraic proof. And the style at the time was to do one and then the other. That's to say that both proofs were supposed to be given, both solutions were supposed to be given in order to solve the problem in the most effective way. So this became the norm, but the problem was algebra is just so efficient and so useful for solving problems that people began to stop bothering with the construction part of geometry. And you'll find that by the beginning of the 19th century, geometers talking about figures as though they're no longer a necessary part of doing geometry. So for instance, here's a citation from Gévin, who says, "We believe it superfluous to accompany this memoir with figures, often more overwhelming than useful in the geometry of space. Figures that we could besides only present in a unique and individual aspect to the reader, who could instead construct and fashion them to his taste, if he judges the assistance at all necessary. We are concerned indeed only with logical deductions, always easy to follow when the notations are chosen in a convenient manner." So you note here that Gévin, who by the way is a full-fledged geometer, this is not someone who's working on problems in number theory for the most part, but he says, "We believe that to include figures was not necessary." And the reason wasn't simply a kind of practical reason, that it was difficult to depict pictures in text. This was true. It was working with publishers to get pictures was tricky, and this is one reason why you find if you look at 19th century or earlier texts in geometry, there's usually a big folio at the end of the book in which all of the pictures are printed separately from the text. They don't flow with the text the way that they do now. You have to go back and look. So this was an aspect of Gergonne's practical life. As a journal editor, he was forced to confront this. But also, Gergonne seemed to think that figures were, as he puts it here, individual and unique. That is, they were subjective. The figure required that the individual mathematician perceive it, and her perception might be quite different than the other mathematician's perception of the same figure. And this was enough to worry about, that it was better, it seemed to Gergonne, to go ahead and forego the figures altogether and just do things algebraically. In fact, that's not quite right for Gergonne. He had a different method of working than explicit algebra, but it would take us too off subject to talk about that. There's a lot to go through here. Maybe more pertinent to current practice, you find this passage from Felix Klein in his text on the Erlander program. He says, "Let us now dispose with the concrete conception of space." Just throw it away. I won't be needing this anymore in geometry. Projective geometry only arose as it became customary to regard the original figure as essentially identical with all those deductible from it by projection. When in the text we designated space perception as something incidental, we meant this with regard to the purely mathematical contents of the ideas to be formulated. Space perception has then only the value of illustration. And illustration was different than proof. Illustration was different than whatever conviction the proof was meant to bring about, whatever evidence the proof was meant to bring about. The figure was there just as a heuristic or as a kind of aid, maybe for the less algebraically inclined thinker, a crutch, you could say. And so this becomes a predominant view, you could say, in thinking about geometry. And this, I think, remains predominant today. I remember going to a colloquium when I was a PhD student in mathematics, and the colloquium, I was a first year student. I was very tired at this point of going to these colloquia where I would understand maybe 30 seconds of the talk. And my teacher said, "Oh, you should come to this one. It's going to be very geometric." Oh, I was excited. I thought maybe this will be the talk that I understand. And I went, and it was as usual, just a bunch of algebra on the board, and I understood nothing. And I complained to him afterwards, and the teacher said, "Oh no, that talk was very geometric." I found myself puzzled by how this could be true. Of course, now I understand this somewhat better, although in many ways one of my philosophical projects is just to fill in that puzzlement that I still feel about that. Why is it that we say that a bunch of algebra is sometimes geometric and sometimes not? But that's, again, a different subject, though this talk today is a part of that big project. Very big project. Klein represents an extreme in this regard. The figure is just there as a crutch. And I think, as I said, this kind of formalist attitude towards geometry emerges from concerns, as Gergonne made clear, about the subjectivity of figures, but they were also thought, the figures, to threaten the generality of mathematics, in that a figure would only represent one particular configuration, whereas algebraic representations could capture an entire range of representations or of objects. Similarly, the evidence of figures was thought by some to be questionable. But also, I think, another strand here was that in thinking about geometry in particular, there became, among mathematicians like Möbius and Peucer, an increased ability to work algebraically with geometry. So, of course, we have analytic geometry in the style of Descartes. This only gets you so far. Nowadays, when we're thinking of algebraic approaches to geometry, we're thinking of the sorts of works that use contemporary commutative algebra. This sort of work it has its origins in a different approach to geometry done, as I say here, by Möbius and Peucer. And as these methods became more powerful, people were less interested in bothering with figures, which seemed to have problems, they thought. But, as ever, this is just one part of the story, and I guess a general program of mine in philosophy of mathematics is to assure people that there is not just that attitude, that there was counter pressure and remains counter pressure today on this approach to thinking of geometry in purely algebraic terms. And one instance of, or one important way in which this counter pressure came out begins here in Paris at the Économade in lessons given by Monge, by Gaspard Monge. So really just down the street, more or less. Monge, an important figure in French history more generally. He was the founder also of the École Polytechnique. Gave lectures to students who were going to be sent off to be warriors, I guess you could say. They were going to be engineers working for the military to create artillery. And therefore, what was needed was a way to communicate these new war machines, which were three-dimensional objects, to the manufacturers who could only work with we didn't have 3D printers, they worked with a piece of paper. And as a result, Monge, being the kind of mathematician, the geometer he was, figured out a way to improve the ability to represent three-dimensional objects in two-dimensional space. And in doing so, he rediscovered the kinds of things that Desargues had been doing 200 years earlier and gave birth to the new level of projective geometry. And Monge explained this take in which, though he was quite aware of algebraic approaches to mathematics, found himself also giving very figure-based constructions. And he explains here, this is from one of his lectures in his 1795, his first year of the Économade. He says, "The object with which we will occupy ourselves is likely to be treated more easily with the help of analysis than by the simple contemplation of the properties of space. But the results to which it leads can be useful to artists who we cannot suppose to be familiar with analytical operations. We will thus try to present these results by employing only geometrical considerations." So one aspect of Monge's approach, which, as I say, is quite figure-based, is that in order for people who are not professional mathematicians to understand the work, it's helpful to see figures, in particular for artists, as he says. And really, the word he uses in French is artiste, but I think what he has in mind is artisans also, the ones who will be creating these machines in the manufacturing workshops of the time. But Monge also, I think, has a further point, maybe somewhat less pragmatic in form. He says that, admitting it is not without a point that we make here the comparison between descriptive geometry, that's his word for what we would call projective geometry, and an algebra. He says these two sciences have the most intimate relationship. There is no construction in descriptive geometry which cannot be translated into algebra, into analysis. That's the familiar kind of translation that we know from analytic geometry these days. But he also adds, if the problems have no more than 3 unknowns, then every analytic operation can be regarded as the script, the écriture, for a show, a spectacle, in geometry. And the idea here is that we can move in both directions. We can start from a geometric situation and translate it into algebra. That's quite familiar, but we can also go in the other direction. We can see geometry as giving life to the algebra itself. It can become, as he says, the script for a show. And he's explicit about this later in the lesson, where he talks about geometry even gives the movements to the algebra. That is, it's not just it's a dynamic thing, not just a static representation like you get in algebra. And then he emphasizes a little bit later in that same lesson, it is desirable that these two sciences should be cultivated together. Descriptive geometry brings the most complicated analytic operations the evidence that is its character, and in turn, analysis brings to geometry the generality that is its own. So, talking about evidence here, this is a word that I think in French has a somewhat different connotation than it does in English. Évidence in French, it means in its most direct sense what is immediate to the senses, in particular to vision. Of course, even in French we can use the term évidence in a more broad way, but in geometry, and in particular in the history of French geometry, this word is generally used to mean something more direct, like like the perceptions that we have so in German, there's this word Anschauen, which has a similar kind of connotation that the word to the word évidence in French, I think. And of course, having this kind of perception, this direct perception, this évident perception, brings with it conviction to the agent who receives the evidence, but that's not the most interesting thing. More interestingly, I think, the agent then becomes disposed to work with the information that's received according to the figurative organization of what's going on. Because I think that figures are a way to organize information. You could say they're a mode of organization. And this is what Monge means when he talks about the evidence, that is, he says, the character of geometry. That geometry gives with it a particular way of organizing the data. And this is, if you think about what I'm saying, this is going to sound in a way pretty facile. But I think that when I came back to the link with my earlier point about my professor in graduate school, who had a big algebraic talk to my eyes and said, this is very geometric. That things were being organized in a different way than it would be if the presentation were, in his view, more algebraic. And I think that bringing philosophical clarity to this distinction between geometric and algebraic, something that's quite elusive, but something that's very important to me at any rate. So this talk is an episode of doing so. What is it about figure that makes it organized in a way that's amenable to a different way of knowing than the kind of knowledge that we get when we have an algebraic representation? And it seems that the development of geometry, sometimes we find algebraic methods that also organize in something like the same way, so that it's not just that geometry represents things in a visual way. But this is all quite mysterious, and though I think as mathematicians we feel the things that I'm saying, but to put them with philosophical precision is a different story. What I want to think about more closely today, to keep the discussion more focused than vague, is a particular kind of geometrical problem solving, as I said, in which we focus on what is evident in this French sense. And Poncelet is a mathematician who gives us a way to do this, and I want to narrate a particular case study of Poncelet's work in order to shed some light on the things I'm talking about. And this quotation here explains the general epistemological view of Poncelet. He says, in ordinary geometry, the figure is traced. You have the word décrit, which is to say there's something manual about it in geometry. One never loses it from view. One always reasons on magnitudes, real and existent forms, and one never draws consequences that cannot be depicted in the imagination or in sight like sensible objects. One stops as soon as these objects cease to have a positive and absolute existence, a physical existence. So this is an ideal where we keep what is given to us in geometry in view, and it's quite literal here. We see it, and we can only see things, as he puts it here, that are real and existent. And here, as I said, I want to talk about a particular case study on this, a case study that I've learned from an article by Gemma Laurenbach, who is a young philosopher, a young historian of mathematics. This article that I'm taking some of this from, which I've quoted here, is an article that just this month won the Montoucle Prize in History of Mathematics for the best history of mathematics article written by a young person over the last 4 years. So this is an absolutely fantastic article, and I'm stealing from it gratuitously here, because what she has found is a case of Poncelet in which the sorts of things that I've been talking about come to life. So as she puts it, part of Poncelet's innovation was the use of projections to bring non-figured and non-obvious figurable objects into the real plane, where they could be manipulated, illustrated, and then become imaginary or infinite while maintaining certain specific properties. Poncelet provided criteria for these invisible objects to be made evident, and thereby count as evidence in other applications. So let's see how this happens. The case study concerns a problem in geometry. The problem is given a conic, to construct a conic sharing a third-order contact with the first. So what is a third-order contact? There's a couple of different definitions. Poncelet understood it as when we have two conics that share a common tangent at a real point and no other intersections. So since conics generally have 4 points of intersection, all the 4 points of intersection are the same in this case. We also can understand this from the point of view of differential geometry, in which we would say that two conics have third-order contact if they touch, and the derivatives of the curvature are the same. But Poncelet's understanding is the understanding in projective terms. And in this kind of situation, to solve this problem, this is a figure from Poncelet's work. Maybe I can use this battered stick to help out here. What he was interested in talking about in this particular figure was the common secant to two conics. So a secant that was shared by the two conics simultaneously. And this is a notion that, though we have from geometry itself, had been rethought in light of algebra, because if we can represent the curves algebraically, we can then set up systems of linear equations to find common secants. But here you'll arrive at solutions to equations that are imaginary and don't have any correspondent in the real plane. And so what Poncelet became interested in was finding a way to represent these imaginary points in geometrical terms. And because secants satisfy some, what you could call harmonic proportions, so-called harmonic conjugacy conditions, we can then use the fact that there is a common secant to these curves, we're working as it were backwards, to construct what he called a supplementary conic. So here is our given conic. Here is what he called the supplementary conic. In this case, it looks like it's probably going to be a hyperbola, in which what we're able to do is take, so here is the common secant. In a sense, you will understand it is common. In fact, this secant here, between points M and N in this conic, the fact that Poncelet used dashed lines indicates that this is in fact an ideal line. It's a line that consists either of imaginary points, or it's in fact a line at infinity. So the dashed indicates that it's not really there. But what he was able to show by virtue of these harmonic relationships is that if there is this secant in this conic, then this secant is a real secant for the supplementary conic. So here you are actually able to see, this is a real line, that each of its points corresponds to the point of this imaginary or ideal secant. So there was a way, using these relationships, to depict the imaginary lines. Here you can see real lines in a real curve that correspond to the imaginary ones. So what we have here is an indirect perception of the imaginary, and for Poncelet, this was very important. We were able to make evidence, that is, to give the quality of evidence characteristic of geometry to what is merely ideal. A second situation in the same general problem is to think about the common external tangents of two particular conics. These common external tangents converge in what is called the center of similitude of two circles or of two conics. And when we have this kind of situation, this kind of common situation, it can be that these centers of similitude are points at infinity. So here's a case where we're thinking about concentric circles. This is again a diagram from Poncelet. When the circles are concentric, we arrive at a case where the lines are continue and only converge at infinity. So this figure is Poncelet's attempt to try to get you to see what infinity looks like, because these lines are meant to be imagined to continue to infinity and to meet there, while still representing the real situation, which is two concentric real circles. And so this uses the same supplementary conic construction that I mentioned before, but the supplementary conic here is not drawn. Here is another step of the construction. So we're working again in a situation where there is a center of similitude. And here we have pairs of lines that are in the two conics being studied that are themselves parallel. So AB, you can see here, and A prime, B prime up there are parallel. Also ED and E prime, D prime are parallel. So these two pairs of lines each have a point at infinity where they meet. And the line that connects these 2 points at infinity, which is of course also a line at infinity, turns out to be a common secant to these 2 circles, because again of this harmonic condition. By the way, it goes back to Apollonius that this condition is satisfied. So what we have here is again a situation where we have 2 circles that share a common secant, but the only way that we could see that common secant would be by recognizing that that secant is a line at infinity. Now this picture itself doesn't help us see it, but this picture is flat. So Poncelet's next move was to think, what if we took this point S and we lifted it up out of the plane? And this is what I have a figure that shows us what is going on. By moving to a 3-dimensional representation, in which the 2 circles are now projections of a common plane through a 3-dimensional cone, we're able to make these tangents and these secants real lines. And I mean here genuinely real lines. So by projective transformations, by taking the picture and lifting it off the plane, by moving from plane to space, we can turn the imaginary and we can turn the infinite into the real and into the finite, and vice versa. We're able to manipulate, by virtue of projections, figures that are that depict what is finite, or rather what is infinite, into depictions of the finite, and vice versa. So by various manipulations, we are able to see these common secants, which are, in some sense, lines at infinity, but looked at from the right angle, they're not. They're real lines. Of course, in doing so, we'll change other things that were real into imaginary. We'll turn other things that were finite into infinite lines. But so, we still have, if we allow ourselves in our geometric reasoning more than just passive regarding of a painting or of a figure to active manipulation of this figure, we are able to see the infinite. This passage from Lorenat, I think, states quite well consequences of this. So she says, one consequence of Poncelet's proposed generality was that formerly finite and real objects, such as a pair of concentric circles in the plane, possessed infinite and imaginary points, 2 imaginary points of double contact on their common chord at infinity. Poncelet's new definitions weakened the boundary between real and imaginary objects, and as justification, he pointed to the diverse modes of existence already present in geometry with respect to infinity and infinitesimals. Poncelet was able to manipulate infinite and imaginary points by a process of translation using perspective, cones in space, supplementary curves, and his principle of continuity. So we can make the infinite real. We can make the infinite finite if we are willing to transform our perception. So this is a way that Poncelet offers us to see the infinite in projective geometry. Now, naturally, these ways of seeing are not direct. It requires that we interact with the figure in ways that we're not maybe accustomed to doing so. The infinite eludes capturing. We will have to find it through sneaky methods. But by working in figures in this new method, we can make the infinite evident, or at least more evident than it is when merely approached analytically. And so for Poncelet, this was to take advantage of the ways that figures can be organized and experienced, which is unavailable to merely analytic representations. And I suppose that's my last slide, and I'm about out of time, so thank you for your attention.